and this does become a hard one to look at beginning to end, because the beginning to end, a lot of stuff changed. And it's become really hard to nuance where those pieces are. If we focus on the chemistry associated with it, we're starting with, what is that, sodium ethoxide and our diester. What would we expect to happen with that, with those two reagents?
Should take the acidic hydrogen.
Step one should result in the acidic hydrogen being removed. Now what?
It would attack or kick out the bromine from the alkyl halide, whichever one.
Okay. So it's going to somehow react with question mark. With a bromine on it. And eject that, right?
Yeah.
So at the end of that step, we would have question mark bound to it. So far, so good? Okay. What happens next?
Yeah, but the negative would take the second acidic hydrogen.
Okay, so it's reacting again with a negative oxygen. We don't have any nucleophilic characteristics or electrophilic characteristics, so more than likely it's going to deprotonate. Sorry, lift that guy off. We have our bond question mark, and then we have a negative charge. What would that negative charge now do? What's that? So it can resonate, which explains why it's acidic, yes. But resonance doesn't fully get rid of it. So what could it do?
Would it form a ring? Maybe?
How does it form a ring? An intramolecular reaction. Okay, how does it form a ring? What kind of reaction are you suggesting we do here? As a hint, you suggested that reaction back here, the purple one. You suggested the exact same thing. What kind of reaction was that? Our green star. Rhymes with bustitution. I have to be real careful with that. Wow. Glad I swapped my consonants carefully. What kind of reaction is it?
Substitution.
Substitution, which means what has to happen at the end.
So substitution.
But to do a substitution, what do you need?
Positive.
True.
A leaving group.
And more importantly, you would need a leaving group. So are we reacting it with another alkyl halide? No, which means where does that other leaving group have to be?
The starting material. Maybe.
Sort of clarify, because we have the diester as a starting material.
I guess maybe the purple structure. Either the red or purple. I'm not really sure. Probably the purple.
And it's kind of hard because we don't have like solid labels here. It would have to be on the question mark. That's where it has to be. So our starting material, the alkyl halide, had to be a dihalide. Had to have two bromines so that it could react twice. Okay. And if it reacts twice, now what happens? The negative comes in, attacks, and we kick out the bromide, right? What would we make? Say that a little louder.
A ring.
We got a ring. Did we want a ring?
Yeah.
We did. There's my question mark, and I'm going to just loop that to make my ring. Okay, what's that? We don't know what that question mark is. We haven't defined it, right? So if it's a single atom, we're talking about a double bond. Okay. If it's multiple atoms, we're talking about a ring. Okay. How many atoms do we want in that question mark? 5? Okay.
Like atoms or carbons?
Fair play. Carbons.
Well, that's 5.
Okay. So we'll modify our question mark now. There's 1, 2, 3, 4, 5 atoms. Is that what you wanted?
4.
Okay. And this becomes one of the real kind of challenging things within this. Let's go back to that starting material where we had that red ring circled, or I circled it with red. Where is this carbon in your starting material? The red dot. Hint, it's not the alkyl halide.
It's on a starting material.
It's on the diester. That red dot is what transferred across, because what's next to it? A carbonyl with an oxygen. Officially going both directions, but what do we have next to it? A carbonyl with an oxygen. So that fits the pattern. That red atom we actually started with on our starting material. It wasn't added by the alkyl halide. It was there in the presence of our diester. Okay. Is this our final product? I guess we should fix this. And we didn't actually specify a product yet. So we could do boop. 1, 2, 3, 4 atoms in our ring, which means what was the alkyl halide? It's the butane, our 1,4-dibromobutane. Okay. Are we at the product yet?
No.
What happens?
One of the sides needs to leave.
Our H3O plus comes through, changes the ester into a carboxylic acid. So we get the technically saponification, if we want to use fancy words. I think that's right. Okay. With a little bit of heat, that structure can rearrange and we can get the decarboxylation. Kicking out CO2 and leaving us behind with the acid. And there would be our final answer. So this is an exceptionally challenging question. Okay, I've seen it show up in a variety of different forms, okay, because we're adding kind of that one carbon. And most people, when they look at that product, go, oh, the alkyl halide had to be this entire piece, because I see carboxylic acid or acid derivatives in the starting material and in the product. But we have to realize that this structure, our starting material, is active not at the carboxylic acid, but at the alpha carbon, or beta carbon? Alpha. Shit, I don't know. One of those. Okay. I don't know that I've heard people reference it. I think it gets called the alpha carbon, to be honest, which gets a little irritating. Okay. Which means that one carbon isn't part of our structure, and we need to be circling these pieces as part of our system. And now what answer sets us up with 4 carbons? We get B and C, and conveniently, I'm looking at things cross-eyed apparently. Okay, we said that structure needed how many bromides? 2, and of course I starred the one with 1. So you're seeing the answer that brings in 4 carbons, but then you also have to acknowledge that it has to react twice within that system. That's nasty. That's the intramolecular reactions. Anytime you're forming a ring, it's real easy to lose track of carbons, and you got to be careful. Think back to the Robinson annulations. Okay? It's real easy to lose carbons or add carbons. So you got to move through kind of carefully and methodically when you suspect there's some kind of ring formation. Make sense?
Can you explain how you got to the final product again? Like how it changed to carboxylic acid?
Yes. Here's our alkyl halide. So H plus in heat protonates, so puts hot hydrogen on our oxygen. The oxygen doesn't want to be positive, so what happens? Water, the remainder of our H3O plus, comes in, does a nucleophilic attack, right? Nucleophile addition, breaks the pi bond, we reform the pi bond, and we kick out the leaving group. The result of this more or less, we've got a couple acid-base steps also associated with it, would be our carboxylic acid, and we still have this ring. Right? We still have an ester. That ester is equally reactive, particularly in the presence of H plus in water. So what happens? Does it again. And now I'm going to get a bit fancy. A little fancy Nancy. Has anybody heard of that book? Yeah, Fancy Nancy. You'd be younger. Be from your childhood. Okay, so we would have the diacid. Okay, this particular orientation, we did a sigma bond rotation about that bond, which brings the hydrogen very, very close to the lone pair electrons on the carbonyl. Those electrons pick up the hydrogen, swing down. That now exceeds the octet on, we'll call it a purple carbon. So to fix that, we shuttle the electrons over to that carbon. So we'd be producing a negative carbon. Can we produce negative carbons? It's a nice, horrendously vague question. Can we produce negative carbons? Yeah? Okay, how stable are they?
Not stable.
Yeah, they're not stable. So if we were to look at this, we might go through and say that this is not a likely reaction because they're not stable, right? Why does it work? We have resonance stabilization through effectively an enolate, though technically it's not an enolate because it is a carboxylic acid. That can resonate up. And what we've got in this large group here is what? What did it act as? It's kind of a hard question. That would be naming the overall reaction. The overall reaction is going to be really hard to name as a chemical reaction because everything's happening intramolecularly. Okay. Are you doing a transfer of a hydrogen? Yes. Is that the only thing you did? Is that the only thing you did? No. So it can't be acid-base. Okay, so you're trying to name the reaction, and all I asked you to do is name this piece. What did this piece act as? We should be able to assign a name to it. It's a leaving group. Okay, we might be, well, carbon's not a good leaving group. It is a good leaving group when it's resonance stabilized. That's kind of the whole point behind this chemical reaction. And what ends up happening is that we then do some acid-base reactions, initiate the tautomerization, and we go to our final product. If we were to add extra color coding behind this, 'cause everybody's got time for color coding. There's that red atom, there's that red atom. Here we said OH. Here we said green. And we've got our final product. So, in and of itself, this question is actually asking a couple things. Number one, just straight substitution reactions. Okay, you're doing an acid-base reaction to do a substitution, backside attack. Very, very, very straightforward. In fact, so straightforward, I believe you saw this question in OChem 1 when we talked about acids and bases. Okay, but in OChem 1, there's no way in hell you would figure out the nucleophile addition elimination stuff, which means in OChem 1, I eliminate that last step. Okay, and we don't do the decarboxylation as a secondary step. So you can see this fully combined outwards, beginning to end. What are we starting with? That structure has a name, this starting material. So I put it in the name, I didn't put it in there. Malonic ester, maybe? I think it's a malonic ester. I'll pull up Google here in a second. And then the decarboxylation is tacked on at the end. So you can see the malonic ester synthesis, which is now just talking, can you do substitution reactions? Followed by decarboxylation. And the decarboxylation is a big one for this particular unit because you're now ejecting CO2. Where might you see reactions ejecting CO2? Biochem could be looking at the production of CO2, which could, though I don't think it does, happen in a similar system. Okay, so you could produce CO2 through a decarboxylation through a biochemical system as well. So it's important to be aware of because it will potentially show up again. Okay, what allowed it to happen? What was critical to the decarboxylation? Okay, so the decarboxylation is right here. Which means everything else can disappear because we don't care about that. I only care about the decarboxylation. What did I need to have to allow it to happen? I need that hydrogen. So if we're going to color code, let's try pink. We haven't used pink. All right, does that stand out? We need that hydrogen so that it can react with the oxygen. Yes. What else? What does that hydrogen have to be connected to? Had to be connected to that oxygen. What did that oxygen have to be connected to? That carbonyl, so that we have a carboxylic acid. Yes. Okay. And then it had to be connected to an sp3 carbon. And what was special about that sp3 carbon? It was going to be a good leaving group. But why was it a good leaving group?
It was next to another carboxylic acid.
Careful.
Or carbonyl.
There it is. It was next to another carbonyl. Okay. Is this piece or this piece relevant to the decarboxylation? No. So what you need to be able to look for when you suspect a decarboxylation, H3O plus and heat is a big red flag, but you can do acid-base reactions with heat. Okay, you can use heat to do an elimination reaction. Technically, is this an elimination? I think it is. Yeah, you form an extra double bond. So yeah, it is technically an elimination. Okay, so what are you looking for? We needed the carboxylic acid functional group, and I needed carbonyl. Do I have a carboxylic acid? Do I have a carbonyl? And you just smiled because what did you discover?
You also need the carbon in the middle in between them.
You also need that sp3 carbon in the middle to separate them so that you can do that resonance stabilization. Okay. The textbook can go through and do a name for this. Let's see if I can come up with it. I think it's a beta keto acid. Okay, and I believe what they're going through and saying in this particular scenario is that this is your alpha position, and then the beta position is there, and you have to have a carbonyl there. So if you're seeing beta keto acids, those can run decarboxylations. Okay? It is very, very easy to fall in the trap of just the primary functional groups. So be careful that sp3 carbon is at least as important. Why not? Let's make this a little bit more challenging. Do I have the sp3 atom? Yes. Do I have the keto? AKA carbonyl? Yes. Do I have the carboxylic acid? Yes. Does this do the decarboxylation? No. Why not? Why does that matter? That puts the negative charge on that carbon. Is that carbon a good leaving group? No. The only reason it worked in the beta keto acid is because there was resonance to stabilize it. If we add an extra carbon there, there's no resonance to stabilize it. Make sense? So you're really looking at the stability of those potential products along the way that help to predict this. We good? Whose question was that? Was that yours, Ivan, or Abby's?
Yeah.
Yours? You happy with it?
Yeah.
Did I flog it enough?
Yeah.
Okay. What's next?
Question after
You can't even tell me the number. I mean, I'm tired, so. Didn't we just do that one?
that. Wait,
Question
24.
Okay. Yeah, I hate this. This is rote memorization. So MCPBA typically makes epoxides with our nonpolar pi bonds. Okay, and in fact, I think just with our alkenes. I don't think we'll do it with an alkyne either. It will react with the carbonyl, and it forms this really goofy intermediate structure that ultimately does everybody's favorite word, rearrange. And as it rearranges, it inserts an oxygen between our carbon and one of the other positions. Okay? That insertion is effectively our rearrangement. So the question becomes, which is more likely to rearrange, a methyl or a phenyl? And if you don't know that answer, you're guessing. Okay? And you could go through and look at this, and you'll see that answer choice B shows it inserting on the methyl side, so we're saying it rearranges the methyl, and answer choice looks like it's going to be C. I know it's kind of hard to see that answer, is having it insert on the oxygen. The other two answers are ultimately just kind of coming up with distractors. We see the epoxide because it does form an epoxide, or a pseudo-epoxide, and that's what initiates all that rearrangement, because you get some oxygen-oxygen bonds that are unstable. So how do we know which rearranges in preference? Migratory aptitude. how do you derive the migratory aptitude? I don't know. I literally don't know. It is something that I found frustrating enough that I tried to look up a lecture to figure it out on where it was coming from. And I pulled a lecture, I want to say from like MIT or Yale, something like that. And their answer did not hold water. So you can make some arguments to stable positive charges, but the phenyl does not form a stable positive charge. And its migratory aptitude is, I think, second highest. So if we look at the migratory aptitude, it starts with hydrogen, then it's phenyl, then I believe it's tertiary, secondary, primary. And what? Oh, and methyl, yeah. So to answer a Baer-Villiger question like this, you have to have memorized that migratory aptitude. It's all it's going to come down to, which I believe is what I said in the lectures too. It's just, you're not going to be able to derive it. You just have to look at it. You just have to have that memorized. Which you get lots of complaints from me saying you haven't explained your work. This is one where I'll be like, you didn't explain your work, but there isn't an explanation that's better than what you've provided. So there are cases like that. Does it work? It's the what? It's C. Yeah. I think it's C. I guess I should pull it up. Yeah, it's C. You know how else you could do this one? Do you know the structure of aspirin? If you knew the structure of aspirin, you could just match the structure that most closely aligns with the structure of aspirin. Oh, speaking of which, I was going to look something up, right? Oh, malonic ester. See, look at that. I was right. It is called the malonic ester. Okay, so you hear it referenced as the malonic ester, and you'll also hear it referenced as the acetoacetate ester synthesis, which is ultimately just ways of naming the starting molecule. Do you really care about naming the starting molecule? No, focus on the chemistry. Don't worry about the name and focus on the chemistry of what's happening within it. All right. Admittedly, I have seen some tests that are like, complete the malonic ester synthesis, and it's just a blank page. Well, thank you. I don't know what any of those pieces are, so we're just going to leave that blank. What next? Why is it not scrolling? There it is. All right, well, we've actually done this mechanism. You could rewind back in the video, and we've actually shown it. So what does the acid do to speed the reaction? Use your words.
Like it makes carbonyl more electrophilic.
Yeah, it's protonating the carbonyl carbon, which makes that carbon more electrophilic, which is why the reaction runs. If the acid protonated the alcohol, what would happen? If we protonate the alcohol, what happens? What is the alcohol acting as in the course of this chemical reaction? A nucleophile. Because why does it act as a nucleophile? It has lone pair electrons. And if I took one of those lone pairs and had it react with a hydrogen, what happens to the oxygen? It becomes positively charged. It is now not nucleophilic. We've lost that nucleophilic character. So affecting the alcohol isn't very promising. Can it? Absolutely. This is one of the reasons why these reactions are technically equilibrium, and I should have drawn that a little bit better. Okay. If we go through and look at the ester structure, we have lone pair electrons on our oxygen and on our carbonyl. Okay. Could it go through and protonate the ester, our blue position? I'm changing it right now. Would that make the carbonyl more electrophilic? Why do I want the carbonyl to be more electrophilic?
Or electrons to easily come in.
So that the alcohol can easily come in and attack. Yeah. What would happen if we protonated that oxygen?
Well, now it's the electrophile, so
Is the oxygen an electrophile? Can it accept more electrons? No, so it is not acting as an electrophile. What's that? It could still be a leaving group, but to have a leaving group, you would need something to push it off. What do you have to push it off? What bond does the alcohol break?
The carbon oxygen.
There's lots of carbon oxygens.
The
Carbonyl, so we
Yes.
go with our pi bond.
Yeah.
The pi bond is the weakest bond. Okay, so if we look at this structure, putting a positive charge on that oxygen, when there's already a positive charge building there, is now going to be an unstable interaction. That's not the most likely place to protonate. Kind of makes sense? Or it's not the proper time to protonate. If we'd pushed the reaction and said, okay, well, let's just protonate it anyway, and had our oxygen nucleophile come in, what happens to our top oxygen? It would be negative. Why is that a problem?
It's an acidic environment.
Under acidic environment, I should not be forming strong bases. Okay? So we can go through and evaluate each of those stages to say what's going on within it. Okay? This is one way to ask that question. The other way we talked about already, doing radio labeling. Okay? Doing oxygen 18 instead of oxygen 16. So yeah, in this case, acid activates our carbonyl electron and makes it more electrophilic. Okay. This is a painful question. Why is it a painful question? You got to read a lot of words to be able to come up with the answer behind it. And in reading those words, what are you more than likely going to read? Or said another way, what are you more likely to read when you read those words? The wrong answer. So it could be very easy to lose track of what's going on within the question because of the volume of words within that. This is why it becomes important to try and identify what that reactivity is before launching into this question. Make sense? What's next?
Can you do 7 on the lead and
Hopefully. And they probably didn't tell you it was intramolecular, did they? Oh, no, they did. That's nice. Okay. So what happens?
we take the most specific hydrogen, which is in between the two carbon atoms.
Okay, which one do we think is the most acidic? So another way, there's a hydrogen here. There's a hydrogen here. And there's a hydrogen here. So if we take that red one off, and here's where we're going to get goofy. Nobody likes doing this, but it's a good idea. Whoop. Whoop. We're going to flip that ethyl up there. Okay, that red one, that's our nucleophile now. That nucleophile now shares with our carbonyl, and we'd make, boom, that structure.
That's a terrible ring.
Why is that a terrible ring?
It's four-membered.
It's a four-membered ring. So you can draw it ugly, and then you can backtrack out 1, 2, 3, 4 carbons. What is the likelihood of forming a 4-carbon ring? Not very likely. So what does that suggest about that red hydrogen?
It's not.
That's not the one that's acidic.
What did it be, the green one?
Okay, why do you want to make it the green one?
Because that negative carbon can react with the carbonyl on the other end, and it would form a 6-membered ring.
Okay, that is an okay explanation. Of course, I'm going to complain about one part. There's our gross bond all the way across. And how many atoms do we have in that ring? 1, 2, 3, 4, 5, 6. 6-membered rings are significantly more stable than the 4-membered ring. It makes more sense to run the ring with the green acidic hydrogen than it does with the red. Why not the blue? It's also going to form a 4-membered ring. Okay. In your explanations of telling me which one was the most acidic hydrogen, I'm a little disappointed, because the explanation you provided for why green was better than red was that green can produce a 6-membered ring. Why is green more acidic?
Is it because it's, when it's the negative carbon, it's able to resonate?
No. Keep going.
It resonates with the carbonyl and the metal next to it.
Doesn't the red one resonate with the carbonyl?
There's more conjugation with the green one.
Okay, so you can run effectively a cop-out answer, sorry. Okay, because you can do this resonance or you can do this resonance and causing those electrons to move around. And we'll fix it real quickly. Why is it the green one? How do you evaluate the acidity of an individual atom, of a hydrogen atom? What do you need to look at? This is a question that you have seen already, probably 2 or 3 times actually, believe it or not, back all the way into OChem 1. You will probably see it on this exam, and you will probably see it on the final. Why is the green hydrogen more acidic?
Is it just because there's one atom pulling on the electron?
Nope. How would we decide? So if we're being asked to rank acidity, what's the first thing that we should try and do?
Sure.
React it so that you have the conjugate base. Now that we have the conjugate base, we can look for charge. So is there a difference in charge? Nope, they have the same charge. Is there a difference in size of the atom holding that charge? Nope. Electronegativity? Nope. Okay, what's next? Resonance. Okay. And what you all gave me isn't wrong. You're all like, oh, the carbonyl can do resonance. But that resonance is identical for both of them, which means it doesn't differentiate them. Are we done with resonance?
The ester can resonate.
the ester has a competing resonance. That competing resonance stabilizes the electrophilic or the electrophilic carbon, therefore making it harder to stabilize the conjugate base. Okay? So when we've talked through ranking different things, and people are like, oh, resonance makes things better. Resonance does not always make things better. Okay? You have to evaluate what's happening within each of those structures to come up with those predictions. Kind of makes sense? We good? And then what you may be experiencing is losing carbons through drawing it out. Or did you have no idea what to draw? Oh, it looks like you had.
The intermolecular stuff always confuses me,
Yeah.
so.
And yeah, that's where you just try and draw it out as best you can. Identify those pieces that we just went through and did, and draw it out as best you can. Very, very easy to lose carbons, so watch out for that. The other thing you might need to watch out for is lone pairs. Doesn't look like you need to worry about lone pairs. I'm not seeing anything suggesting lone pairs. Okay, what's next?
26.
What's that?
26 on the opening there.
Oh, look at that. It's like the exact same question we already looked at. Use your understanding of the mechanism for this reaction to predict the products. This one's a more straightforward mechanism because we aren't doing anything with acids, so we don't have to stress about acids, but we do have to stress about how this reaction works. So how does the reaction work?
I think the OH acts as a base.
The what?
The OH acts as a base, I think.
So if the OH is acting as a base, where's the acidic hydrogen?
I think it's the one that's at the far left.
Okay. So we could make a nucleophile here. Okay, and if we've got that nucleophile now, what could happen?
Okay, so maybe it reacts with itself, like this starting.
Cool, a second molecule. Yep. And so what you're running is effectively an aldol reaction where you've created a carbon-carbon bond. Go through and look at all your answer choices. Do you have any carbon-carbon bonds? Okay. So while that is a possibility, as we just addressed with the ester, okay, the ester isn't particularly likely, okay, to be acidic. Whoops, as I use an eraser. Okay, so that hydrogen is not particularly acidic. Okay, we can still run that reaction, but we can run that reaction when the quote-unquote base that we use matches the leaving group, so that we don't get nucleophile addition elimination chemistry. Do they match? No, which means more than likely, what do we get? Addition elimination chemistry. So, what happens? The OH attacks the carbonyl. Now what happens?
Oxygen comes in negative.
We break the carbon-oxygen double bond. Now what happens? Comes back down and kicks out that group. So what do we end up seeing? We're going to see this CH3C carbonyl bonded to OH, and we'll see this OC, CH2, CH3, CH3H as a minus. Okay. In this case, what would happen? What functional groups did you create?
Carboxylic acid.
A carboxylic acid and
Ester.
an alcohol, okay, or the conjugate base of the alcohol. That's effectively a strong base, so what does that strong base go through and do? Deprotonates the acid. We would get the negative acid, and then we would get our hydrogen on this oxygen. As we ran through and ran that reaction, it did not intentionally show where the 18 is. Okay? It's a game of cards. Where did the 18 end up? It's on the alcohol. So now what do I have to do? Figure out chirality, because we got lots of wedges and dashes. But let's think about that chirality. What happened at the atom that was chiral? Nothing happened to it, which means it stays the same. So I now just have to go through and find the species that matches this structure. So there's an 18, so that one's wrong. There's an 18, that one's wrong. And then I have to find the structure that matches this one, where I correctly label all the wedges and dashes that had not changed. Of course, what's potentially obnoxious about it?
They changed in the answer.
All of those things rotated around and changed your viewpoint on it. You mean kind of like OChem 1, our Unit 1 or 2 exam. Yeah. So you're now responsible for aligning it. What's the easiest way to do it? It's personal preference. Some people like going through and assigning R and S. So you could go through and say we've got an oxygen, an ethyl, a CH3, 1 to 2 to 3. That's going clockwise. The hydrogen was aimed away, so that would be R. So now I could go through. I would just pick A as a random answer and just try that. The oxygen 1, 2, 3. Which way is that turning? Clockwise, which means R, which means dang it. What happens with the other one? 1, 2, 3. Still going R, except we're looking at it backwards. This one would come out as S. Kind of, sort of. So it's, do you understand the mechanism? If you don't, you get it wrong. Okay, that's fine. Okay, this is one of the reasons why I push mechanisms a whole lot, because there's ways to deal with looking at those mechanisms. There it is. And then you have to kind of ask yourself where the chemistry happened when we evaluate that chiral atom. Okay, again, we add a random thing and everybody goes, oh my God, I can't figure it out anymore. It didn't do anything, don't worry about it. Keep it the same. Keep it constant. Does that make sense? Okay. Next question. This one looks familiar, huh?
Yeah, it was on the last one. So
Yeah. It keeps showing up. Why do you think it keeps showing up? People keep getting it wrong. That's why it keeps showing up. Okay? So process it. Okay? Admittedly, that MTB in the practice exam is a little weird, but we can pull it out here. Okay? I want to make this. What bond was most likely to be made? Okay, said another way, is it most likely that I made that carbon-hydrogen bond? Why not? If that was the bond that I made, what would my starting material look like? I would have a negative carbon. Is negative carbon a good thing? No, that would be a problem. Or I'd have a negative hydrogen if we flip it. Either way, that was a horrendous bond to look at. What bond should I look at?
Carbon-oxygen.
Why should I look at the carbon-oxygen bond? No. I'm also looking at an alkane, and we just said looking at the alkane was irrelevant. Why should I be looking at the carbon-oxygen bond? Which is already a misleading statement. That carbon-oxygen bond is already a more active bond. Why? What kind of bond is it? polar covalent. So when we're trying to go through and do any kind of reaction, what we're looking for is those high charge things, right? I did say that the ether bond was a dangerous statement. Why is it a dangerous statement? What is the ether bond?
It's ether, so like 2 carbons. Is that right?
There's 2 carbons. Is that an ether?
We'll connect it to an oxygen.
Is that an ether?
That is.
No.
Carbon, oxygen, carbon.
Carbon, oxygen, carbon. This is what makes an ether. Okay, that is the functional group. Okay, but if I say the bond is, there's a bond, is that an ether? No. To make an ether, what do I need? I need a second carbon, which means there are 2 carbon-oxygen bonds. And when I design the synthesis, I have to decide which of those 2 bonds I want to look at. Do I want to look at the red carbon-oxygen or the blue carbon-oxygen? Okay. And if I don't know, what should I do? Draw it. If I was going to look at the red carbon-oxygen, that bond would break, right? Where would the electrons in that bond go? To the oxygen. Great. And so our oxygen would be negatively charged. What happened to the carbon? It would be positively charged. Great. What now becomes a problem?
Put the carbon cation near the leaving group.
Okay, and we can put on a leaving group.
And then it would have steric group.
Why does steric hindrance matter?
Because the oxygen needs to go kick out the leaving group
Why?
to
Why does it work under SN2 conditions?
Strong base.
How do you know it's a strong base? And sorry, not strong base, strong nucleophile.
It's negative.
It's negatively charged. If this is strong, that needs to be, what am I trying to write? Strong, this is our SN2. And if it's going to run under SN2, what should the substrate be?
Non-sterically hindered.
Not sterically hindered. Is my substrate sterically hindered?
Yes.
Yes, which means
Not good.
that's probably not a good answer. Let's take a look at what happens with B. We go through and do B, we're going to do effectively the same thing. We want to split it. How do we want to split it? Where should the electrons in that blue bond go? Onto the oxygen. Why to the oxygen?
It's electronegative.
It's more electronegative than the carbon. So our carbon, which I'll have to draw as a CH3, would then be positively charged. Okay, we don't like that positive charge, so what do we need?
Negative.
We would need our leaving group. We now have a sterically hindered nucleophile, yes, but is the substrate sterically hindered? No. So between these 2 paths, which one's the best path? The second one. The first path would more than likely undergo actually E2, because we have a tertiary leaving group with a strong base. Okay? Which then means we have to go through and find the answer that closest aligns. In this case, we're only looking at the alkyl halide. For the blue one, it's CH3Br. Why do we pick Br?
stable as a
It's a good leaving group. Why else do we pick Br? Harder question. It's what the Williamson ether synthesis uses. Okay? It's the definition of the Williamson ether synthesis. Okay? You didn't need to know that because did any of the answers have that as an issue? No. Okay? And officially, it doesn't have to be bromine, but a halogen, so chlorine, bromine, iodide.
Could you explain what the dual was correct?
We still have a strong species here, which would suggest 2-type. If we look at the substrate is 0 area. What substrate or what mechanism favors zero-area substrates? SN2. Any others? No, actually, it's just SN2. It is the only one that you can do in an SN2 fashion. You can't do an elimination because there's no other carbons to pull a hydrogen from. So the elimination's off the table, so it's your only choice. Kind of makes sense? Synthesis is dangerous. You have to watch out for synthesis. Invariably, when you look at a synthesis reaction or sequence of reactions, you will have at least 2 polar bonds. And what you've got to try and decide is which polar bond is best. That's the whole point of training you in synthesis, is how do you break down a structure to get back to those starting materials. Note, what arrows did we use? Yeah, that was the retrosynthesis arrow. We were thinking backwards. Okay. So depending on your kind of comfort within those systems, you could opt instead to use a normal arrow. Just make sure you're going in the correct direction, which does sometimes become a problem with retrosynthesis, as students will start thinking forward when the question is asking backwards. So make sure you're careful in reading those. Next. Okay, I heard an U, thanks. Okay. I am not a fan of questions being formatted this way. If we're going to look at spectroscopy, let's look at the spectra. But ACS goes back and forth. Sometimes they'll just give you the data, sometimes they'll give you the spectra. So since they're giving you the data, you have to be able to interpret it, and you need a little bit of practice with that. So, ta-da, there it is. So what do they give you? And if it has a singlet at 2.1, is that a typo? Oh, no, never mind. What does it mean? Sorry.
No neighbors?
It has no neighbors. Okay. Chemical reaction ran. Okay, and it's only partially evaluated. Dang, that's rude. What do we see in part 2? We see a leaving group, which ultimately means we've got a CH3 that is partially positive, which means what needs to be the results of step 1? We need to create a negative. We need to create a nucleophile that would react with that carbon. Okay. Where could I create a nucleophile in that starting material? Okay, the oxygen has lone pair electrons. If that oxygen went through and shared electrons, what would happen? Right? Do we want a positive oxygen? No, so that's potentially problematic. We could do resonance, shuttle the electrons up, except then what does that create? A positive carbon, arguably a worse structure because it's missing its octet. Okay, and we have no other source of electrons because the step 2 was providing an electrophile. If we push on your methodology a little bit harder, if this was the reaction, did you need a step 1? No. So step 1 has to do something. Step 1 should give us a nucleophile. If the oxygen was already a nucleophile, there's no step 1. So, we can push on that. You could go through and add a carbon nucleophile. Now what happens? have the negative oxygen after step 1, and what could we do to finalize that? Step 2, and put that carbon on. So that could get us this potential structure. Okay. There's not a whole lot of information in the spectroscopy. So we don't know if there's other signals. We just know we have a singlet at 2.1. Okay. Would this be a singlet? Yes. That would be a singlet. A singlet connected to a carbon, connected to an oxygen, would shift downfield. Probably in that 3 range. Why is that problematic? We need to be at the 2. Okay. Is this a singlet? It is, also tied to this one. Okay, both of those would be singlets. Those are even further away from the electronegative oxygen than our purple one is, which would shift it down lower, so maybe. Okay, so we've got enough information there that what could we try and do? Yeah, let's look at the answers. You started it off with a carbon nucleophile. Do you see a carbon nucleophile? Nope. Dang it. Oh, okay. Why do you want to form a carbon nucleophile?
Well, there's resonance stabilization. But then
That would explain how you get the nucleophile, yes, but why do you need a carbon nucleophile?
it's at the 2, which is the
To attack step 2. So if you could get a carbon nucleophile out of step 1, that could work out. Okay, and if we push on that, what reagents are we adding for A, B, and C? Yes. I mean, no, actually it's not H minus. It's N minus. Lithium diisopropyl amide. What does NaH act as? I'll accept that. It would be H minus, which is what I think Josie was whispering, which is a base. What is the top one? O minus. What can all 3 of those atoms do? They can all act as bases.
well, doesn't NaH like deprotonate everything?
No. It can only deprotonate one thing at a time.
Well, isn't like NaH a super strong base to like?
It is indeed. And it would form H2. Which hydrogen is the acidic hydrogen? I'm struggling just as much as you. We talked about resonance, so we're talking about the alpha hydrogens. We have red and blue. Do they have a difference in acidity? No. So how would we know which one to remove? What would be the product? Does it look familiar at all? Somebody laughed. Is that because it doesn't look familiar?
It's just like system strands.
Nope.
Keto.
These are still, they're both technically ketoenols.
Is this what 2 versus 4?
Related. I don't want to write it all out. It's kinetic versus thermodynamic. So if we look at those base strengths, H minus and N minus are both kinetic, okay, irreversible. Okay, so where would they deprotonate? They would deprotonate our kinetic one, which color coding, oh man, I just screwed up the color coding up the yin yang. okay, would be our kinetic. I'm just going to erase that. No one ever saw. Okay, and if we evaluate our resonance structure, the one that is useful would be this guy with the negative charge, which would mean where does our hydrogen go? Or sorry, our CH3 go? To that spot. So the product we get is if we run the other one, our best versus our useful, we've got our CH3Br, electrons attack, kick out the bromide. Why did I change the colors? Oh my God. There's our new CH3. Okay. This one was our thermo. This one was our kinetic. Which technically gives you your answer. We want the thermodynamic, yeah. Which one's thermodynamic? A. Okay. B and C both do kinetic. So this would have to be a select both, or select those two kind of an answer, and leaving the A answer choice off. Wasn't phrased that way. A is the only one that makes sense. Again, review of Unit 2. Make sense? Questions about it? Do we want to do another question? You could always get out early too. No, because I feel like crap. What is the product of the following reaction? So what do we see?
There's the negative O. It's an ester.
We have the negative oxygen. We do have the ester functional group.
I'm pretty sure there's no acidic hydrogen, so that would have to attack the carbon.
If it attacks the carbonyl, what carbons are connected to the oxygen? 2. It would replace 2 carbons. Would it result in a change of structure? No. Why do you think there's no acidic hydrogens?
Like just doing the same. Like just remaking the starting material.
If the oxygen acted as a nucleophile, I agree. Why are there no acidic hydrogens?
So then it reacts as a nucleophile.
Answer my question. Why do you think there are no acidic hydrogens? To be acidic, where should they be located? Where were the acidic hydrogens in question 28? Where were the acidic hydrogens? Yeah, actually, we didn't do that one. Yeah, now we gotta go for. No. Diball. So we haven't done very many acidic hydrogens, apparently. Oh, there's one. 18 was acidic hydrogen. Okay. Where are acidic hydrogens? The naming is weird. I think it's alpha. Where does it need to be?
Carbon next to a carbon.
So if we look at our carbonyl and we go that way, oh, there's an oxygen, so that can't possibly have a hydrogen on it. What happens when we go the other way? We have a carbon. Carbon with how many bonds? 3, which means there's an implied hydrogen. Do we have an acidic hydrogen? Yes, we do have an acidic hydrogen. Okay. So your argument is flawed because you said there's no acidic hydrogen. There absolutely is. Okay, so now what happens? Sort of. We make the negative, and then what you're saying is it reacts with itself. And if we go through and take a look at our answer choices, 2 rings, there's 1 ring, 2 rings. 3 out of the 4 answer choices are showing us 2 rings, which would suggest it's reacting with itself. Okay? So we could go through and try and draw that out. It's going to be really ugly. Let's see if I can pull this off. Could be some straight rabbit out of the hat kind of stuff. That's one of us. There we go, right? Is that one of the answer choices? It is. Is it the correct answer choice? Ooh. Why is it not a correct answer choice?
It's a Claisen reaction, right? It needs 2 acidic hydrogens in order to be able to work.
All of those steps, particularly here, is very sterically hindered and unstable. So what can happen is that your oxygen, CH2, CH3, can come back in, attack, break, and kick that back out. So it very heavily favors the reactants. For the Claisen to work, you have to run one more irreversible step. That one more irreversible step is to remove a second acidic hydrogen. That second acidic hydrogen does resonance within those carbonyls, which drops the energy of that intermediate, therefore allowing the reaction to occur. Okay? Arguably, that's the reason we call it Claisen, because aldol wouldn't have cared. Aldol would have just run it and been happy with it. Okay? But that second alpha hydrogen becomes critical for the Claisen reaction actually working. The Claisen is the aldol. They're one and the same, except you're starting with an ester instead of an aldehyde or a ketone. The chemistry is identical. You just have to be aware of that kind of secondary step within it. So what does that mean for us? If we don't have that acidic hydrogen, what happens? Or that second acidic hydrogen? It reverts back to the starting material. And our answer becomes C. No reaction. Okay? Which is really bothersome because people, well, why don't you call it no reaction? A reaction did happen. So you can't really call it no reaction. It did react. It just reverted back to the starting materials. Okay? So that becomes one of those kind of extra pieces because they'll draw structures and say which of these will react in a Claisen reaction. Okay? Mildly irritating because they're asking you to have that information named. If they've done it right, they'll say which of the following reacts in a Claisen reaction in the presence of the ethoxide. Right? So they'll give you the base so that you have something to work with and you don't have to have the overall reaction memorized. But you do need to know what sets it apart from the aldol. Make sense? Okay. Then with that, we're done.